All right, we are back. Um, Hopefully you didn't have a panic attack at the end of that lecture. Um, it's a lot. I know it's a lot. I honestly, I do understand that it can be very daunting when you look at those formulas, but trust me that we will help you through it and just take your time. Okay, that's really the two biggest things that I can do. And don't have a panic attack while you're literally doing the question. So we're gonna continue on. I need to share the screen with you. Oops. All right, so coefficient of determination. So you do your calculation of R, and then what? Well, that means you have found a correlation, which demonstrates a relationship between two variables. I like that blue color better. And how do you interpret that? So what does it mean when you get a correlation? How do you interpret that? Well, we're going to learn a coefficient of determination, which is very simple calculation compared to the other one. And it's literally just R squared. You're going to take the R that you calculate, you're going to square it. Okay? So for a Pearson R of 0.6, R squared is 36, right? Because you're taking your R and you square it. 0.60 times 0.60 on the calculator is 0.36. So although it's a very simple calculation, conceptually, it's a lot harder to interpret. It's harder to make sense out of what it is, right? So let's look at our previous example. You know, you have all those subjects, you have X's and Y's, you have Carol all the way down to Liz, okay? When you look at those distributions of scores like this, right, there will always be differences among the scores on X's and Y's. There's going to be variability on the X's, so there's variability here, and there's variability on the Y's. Not everyone has the same X score. Not everyone has the same Y score. So there are variability both between X and Y and within X and within Y. So there's two types of variability, between and within. And I just lost the PowerPoint. So let's try that again. All right, I'm going to pause our recording and I'll be right back. All right, so I am back. And I should have done this ahead of time, but I did not. So when you look at those different scores, X's and Y's, there's variability within and there's variability between. This is what we call variance, right? So even if you measure someone's anxiety scores, my anxiety score is not going to be the same as Andrew's anxiety score, right? We're going to have different anxiety scores for whatever, whatever measure you're going to take. And so those measures relate to not only variability within a given idea or concept like anxiety, but also between if we measure a different score or a different measure. So an important question when evaluating a Pearson R is what percentage of the variance on one variable is accounted for by the variance on the other variable. So the phrase this in something that might make more sense. We may be interested in what percentage of the variance of GPA is predicted by variance of ACT scores. So your ACT or SAT scores may relate to your GPA, but how much? It's not everything because it would be the same measure. So there's slight variations, but we can measure that and examine that by doing R squared. R squared is a proportion of a variance accounted for by measure of 1 by calculating that proportion for a given variable and the relationship between those variables. So the higher the relationship, the more variance that is being accounted for. So R squared, if it was negative 0.77, you square that, you get positive 59. You can multiply that by 100 to obtain a percentage. We talked about how correlations, you can't multiply by 100 to get anything. But with the variance accounted for, you can. In fact, that's what you have to do. So the variance accounted for says how much of X is accounted for by Y. How much of your GPA is accounted for by your ACT scores? How much of your anxiety is accounted for by how much sleep you're getting? How much whatever is accounted for by something else, okay? The more highly correlated the two variables, the more variance that is accounted for in one variable by the other. If you have a perfect correlation of 1.0, square that, it's 1 times 1 is 1 times 100 is 100%. But that's usually not the case. If you are explaining, for example, a correlation of 0.77, which is 59%, that means there's a large chunk of that variability that is not being accounted for. Well, what is that other chunk of stuff? That other chunk of stuff is other variables that have a role in those in calculating that relationship, right? So if you're looking at ACTs and GPA, maybe it is how much you study. Maybe it is whether you have a tutor. Maybe it is how your general level of academics. Maybe it's your exposure to different concepts. All those things go into making up the 100% value of something, and that's not what we're looking at when we're doing the correlation between two variables. We're just looking at one other thing, and so it's not going to be a 100%. So what does that really mean? It means if we're trying to predict how subjects score on variable Y, and simply put all the subjects on slips of paper, draw a name, and declare that the person who draw will perform the best, and so on, we're going to find that we're wrong every single time, right? In the long run, we're going to be wrong, but we can figure out how much of that variability we can predict by looking at that relationship. Look at it this way. You have an X variable, you have a Y variable. The more overlap there is between these two variables, let me change my pointers. Let's do in color. Let's do red. Right now there's this overlap here, which is overlapping between those two things. That is how much of X is being predicted by Y. When I go forward, the more overlap there is, the bigger that chunk becomes, right? As more overlap, that overlap becomes even more. And so the more overlap relates to the relationship. The more closely overlapped those two things are, the larger the relationship, the larger the correlation between those two variables. So this is not related at all. This is a small correlation. That's a bigger correlation. That's an even bigger correlation. And eventually we could have a perfect correlation. So once we know our Y, it is X. And so that's what we're looking at when we're looking at variance accounted for, is how much of that overlap exists between those two variables. Our accuracy in prediction, if we have, when we looked at before, is about 59%. The flip side of this is that 41% of the variance is not accounted for. So 41% of what's going on, we're not accounting for by looking at these two variables. There's other things that are playing a role. This means we still have room for improvement in our ability to predict what is going on. If we can account for more and more of the variance, and we can become better at predicting scores on one variable from the scores in the other. That is one of the main goals of correlation. So if you look at the values here, so if your R is 0.1, if you square it, it's 0.01. You're accounting for 1% of the variability. As you go up, 0.2, now it's 4%. 0.3 is 9%. 0.4 is 16%. 0.5 is only 25%. Right? Look at that value right there. If you have a correlation of 0.5, which we consider a good correlation in psychology, you are only accounting for 25% of what's going on by looking at that variable. That's it. That means 75% of the variable is still not clear of what's causing those effects. 0.6 is 36%, 0.7 is 49%. So you're not even at half of the variability accounted for, and you're at a correlation of 0.7. Because there's other things that are causing these effects. There's other variables that have a role to play in this thing. 0.8 is 64, 0.9 is 81, and 1 is finally 100%, okay? In this table, the small values of R shrink dramatically because it is exponential, right? So we need to be more cautious when interpreting small values of R because there is so much more variability that plays into that. These are further from perfection than they may at first seem. You have a 0.5 correlation. You're like, hey, wow, I got a 0.5. It's only accounted for 25% of what's going on. That means 75% of what's going on, you're not quantifying. And so you have to be careful when you're doing this. You have to be careful when you're making those interpretations. Okay, so that is the coefficient of determination. That is how much overlap there is between those variables. What happens if you want to, okay, well, so in this situation then, if our X and Y are related, what happens if I want to know more about what is causing these effects? Well, I can add more variables and I can do multiple correlations. We can use more than one other variable as part of this relationship. This is going back into a little bit of a complex formula. I'm going to show it to you today. It may take a little bit for you to make sense out of this, but I'm going to show it to you anyways. So we're often interested in the extent to which two variables in combination predict a third variable. So maybe high school GPA and college admission test to predict college GPA. So we're looking at two things, right? We're looking at high school GPA and college admission tests. And how does that predict your scores on in your current college GPA? For cattle, we have statistics called EPDs, where we look at more than one variable to make predictions as to what the young of those animals will do. So you breed two animals, a dam and a sire, a female and a male, and their offspring will have qualities of both. An EPD is a statistic which tells you the relationship between those types of things. So we look at birth weight, we look at calf, sire, dam birth weight, we look at how much the sire, the dam weighed at weaning, so how big they are when they stop drinking their mama's milk, how big they are when they're a year, how big they are down the road, how much their mama milks. All those things are variables that we consider because one of those variables by themselves tells you only part of the story and a very small portion of the story. So we look at multiple variables altogether. So going back to that GPA example, we might look at three variables: college GPAs, high school GPAs, and then college admissions tests. We want to be able to predict, and we hope we're going to be able to predict variable one. So let me start again. So we're going to have to name one of the variables that we're going to predict, variable one, and then the other two variables become variables 1 and 2, okay? Doesn't matter which one, 2, and 3. So we're going to try to predict GPAs. We're going to use high school GPAs and college admission tests. All combinations of these three variables and the relationships are needed to be able to do a multiple correlation. So we need to know the relationship between variable 1 and variable 2. So 0.55 is the relationship between GPAs, college GPAs and high school GPAs. And then it's between 0.4 between college GPAs, college admissions tests, and then the last one is between high school GPAs and college admissions tests. The reason you do all three is that you have to figure out how these two things are related themselves to take out those effects, because there's overlap between those things as well, okay? The value of R12 indicates how well high school GPA predicts college GPA and so on for R13 and R23. I will label these, I'll put them in order. You won't have to worry about doing that. What we're essentially doing in multiple correlation is determining how well each predictor relates to the variable to be predicted. And then how much overlap exists between the two predictors. That's what we're looking at overall between these variables. The variable or the correlation, the formula is this, right? And these are just the actual R values that I give you, so you don't have to calculate any of those. And then you're just squaring those and multiplying them together. It can be a little bit of a challenge doing this formula, okay? So if we use the formulas that we had, R squared for the 1 and 2, it's 0.55. We're going to square that. R13 is 0.44. We're going to square that. Then we're going to minus 2 times each of the variables together, right? So you're taking 2, you're multiplying by this one, you're multiplying by this one, and you're multiplying by this one. This is where people mess up. This part of the formula right here is where people mess up. That's not really working well. So that's where people mess up is right there. The easiest thing to do is leave your negative and then multiply just 2 times this times this times this. You just keep multiplying. So 2 multiplied by 0.55, multiplied by 0.44, multiplied by 0.38. And that will give you the answer that you need, which is up top 0.184. Okay, 0.55 squared is 0.303, 0.44 squared is 0.194, and then you minus that other one. And then on the bottom, it's 1 minus that other thing squared. Again, watch your square roots. You add all those up, minus that negative number, and you get 0.313, right? And that's all over 0.856. Then you take the square root of that. You're going to come up with a value here. I don't know why it's working like that. that demonstrates the relationship between that. This, again, is a correlation. So now you're back to having a correlation between all three of these variables. So when you add all these things together, right, when we go back, well, each one of them predicts 0.55, 0.44, 0.38. When we add all three of these things together to predict things, we gain a little bit of correlation, and now we're predicting at a 0.61, right? So we gain a little bit because we've added in other things. So now we account for more variance because now we're looking at other variables that play into this factor, okay? Again, this is a complex thing. Don't worry if it doesn't make 100% sense at this point. I'm more interested in you understanding original correlation than this one, but this one, there will be one of these on the exam. So for all practical purposes, we interpret R the same way, between -1 and +1, and its values that, closer to 1, the stronger, closer to 0, the weaker, and so on. When you add them all together, you're going to have something called big R, right? That's what we're dealing with here is big R. Big R is the combination of all these other variables. And you can do more than 3. You can do 4, you can do 5, you can do 6. We're never going to do anything more than 3 in this class, but you could. And this is just the amount of overlap that exists in these variables and how much they're all predicting this other variable. So how well all three of them predict each other together, okay? So not only does X and Y come together, but now X, Y, and Z are all overlapping. There's overlap between here, between Z and X and Y. There's overlap between X, between Y and Z, and there's overlap between Y and X and Z. So there's multiple layers of overlap. And so you're taking out the multiple layers that are all three, and then you're seeing the unique contributions of those three variables. Again, conceptually very difficult. Not hard to calculate, but the formula can be challenging in a couple of those spots, okay? So these are the variables here. Those are how X and Y relate to each other. That's all three together. That's Y and Z, and then the last one together. The greater the original correlation, the better your predictions, right? So here's one more example that I'll let you guys work through if you need to. These are the multiple correlations between calf and dam weaning weight. Again, this is made up data. So the relationship between the mama and the calf and their size and so on. And then that runs through all the questions there. So if you can do that and come up with the right answer, you got a good understanding of how this formula works. Again, you are not going to learn these statistics unless you do this stuff, unless you sit down and work it from scratch. It's going to be really hard to learn how to do it, and it's going to be hard to do well on those tests. All right, so just to finish up, Pearson R can be calculated using this formula here. It's a big, ugly formula. Take your time, work on it slowly. To complete this formula, be sure to use the table technique. You're going to have to. I want to see that table. That counts as your work. If you don't show me your table, you're going to lose points. Remember, the sum of x squared is not the same as the sum of x bracket squared. These are different numbers. Remember, it does not matter which variable you label as x and which is y. You'll get the same thing. Just remain consistent. As a check, remember that you will never have a value bigger than +1, and you'll never have a value smaller than -1. You're going to have that boundaries there. Squaring your R tells you how much variance in one variable is accounted for by variance in the other one. So that's R squared. And big R is when you have more than two variables that you are correlating. Okay? All right, so that is all for today. That is everything. The homework will be due on Wednesday to Andrew. Hopefully I'm back on Wednesday and we're just trucking along and we'll answer questions. If not, we'll keep doing this. So let me know if you have questions. Email me if you have any questions. Hopefully your exams, you can see those. Don't panic if your exam scores are not as big as you, or not as good as you would have liked. It's only 10% of your score. And it's easy to come back even from a low score on that first test. That is not uncommon. And there'll be some bonus opportunities. So keep that in mind, okay? All right, that is everything. We're not doing that for right now. I'm gonna stop recording and have a good day. We'll see you on Wednesday.